is there are engineering methods and procedures to make use to find out by traversing anemometers on the exit of the fan in cooling towers, on inlet of the fan in the forced draft airframe coolers, or on the outlet of the fan on the induced draft airframe coolers, or the air-cooled condensers that nowadays are being used for dry cooling systems. So this shows a little bit of a laborious work that is involved in trying to do the measurements for a particular installation. This is what we've been talking of. The typical components are all common in both of them. You can see everything is there in both. One is an induced draft with the fan on top of the tube bundles. The other one is a forced draft. As the name suggests, the right side one forces the air through the bundles, whereas the left side one, the induced induction or suction of the fan is there from bottom. So it's inducing the air, and hence the name in the fin fan coolers. I'm sure you're all aware of this. There are various advantages and disadvantages of the installations. I would not like to go into more detail of this because already installations are existing. These are more required for basic design options if one was trying to do it. The main thing comes from the fan selection here. As you can see, the total motor shaft power that is being consumed is a function of the fan efficiency and speed reducer efficiency. The existing system, whatever is there, you have an airflow in cubic feet per minute or meter cube per second or meter cube per hour, as we call it CFM, cubic feet per minute, or some people call it as ACFM, actual cubic feet per minute. In the data sheets you find these words being used. The total pressure loss, this is different from the static pressure that is being specified by the common suppliers of these fan cooler systems. The total pressure is a combination of the static pressure as well as the dynamic or the velocity pressure. So that is either in inches of water or in millimeters or pascals or bar, as we call it some of the places. So now you can see here, for any duty condition, your actual airflow is fixed, your total pressure loss is fixed. Both being constant now, you have only two things at the bottom to reduce your motor shaft power. That's your fan efficiency or the speed reducer efficiency. We are not thinking of anything in the speed reducer efficiency because we are hoping that your system or drive is just in condition in a proper way. And this is where the fan efficiency is what we have concentrated on, and hence we have been able to improve the fan efficiency, and hence the motor shaft power has been reduced, and that's how they become energy efficient. These are some of the graphs that are used basically to find out what kind of powers are required from the fan selection with the horsepower requirements. This is a specific thing which actually decides how far away is your ideal blade design from the thing that you're actually operating. Ideally, what we need is a very uniform velocity along the length of the blade that you can see. The central darker portion is the hub, the other portion is the blade that you see. But in practice, you can never achieve this absolutely theoretical uniform velocity. In these blades, obviously you need something called an aerofoil to do the useful work. Just like all these aerofoils are like the aircraft wings that you see. Obviously what happens is the aircraft doesn't take off unless it runs for a longer time. That is when the speed of airflow across the wings is good enough to give it the necessary lift. So once it gives or it produces the lift, you have the aircraft taking off. In a similar way, in the case of the fan, what you have is, you have the aerofoils which are used on the blades, and these blades produce the lift downwards. And hence, by a simple Newton's third law of motion, there's an equal and opposite reaction. So when the thrust or the aerofoil lift is being made to act downwards, there is an opposite suction of the airflow, and hence the fan sucks the air and pushes it through the forced torque or the induced torque fin fan cooler systems. So this is where the aerofoil design is most important, to be able to get the actual lift or the airflow. Whenever there is an aerofoil that is used, just like how there is a lift, there is also a drag, which both are associated with the aerofoil. The drag is a bluff body, like suppose a fatter person like me wants to run, he has to overcome more resistance. A thinner person would need a lesser resistance. That's what we are calling in terms of drag. Okay? So the drag is the one which actually goes back to the motor in the power consumption that has to be overcome by the fans. Okay? So just because you're able to give higher lift, it doesn't mean you can cut down on the drag associated with it. So in any aerofoil, the lift as well as the drag both are completely interrelated. So the research that has been done is in trying to get the best possible lift to drag ratio, as we call it. So any aerofoil which has a better L/D ratio will give us more useful work. So you can see here a simple calculation that shows from the tip of the blade to the center of the hub. You can see that down there you can see a simple triangle there which shows the direction of rotation and also which shows the axial velocity U component. So as you can see at the tip of the blade, we are trying to have V, which is the velocity output from all these locations. As you can see at the tip runs faster, whereas towards the closer point, the tip runs at a lower speed. It's simply the circumference multiplied by the RPM. So obviously at a lower radius, the aerofoil moves at a smaller speed. In the same blade, at the tip portion, it moves at a higher speed. So as you can see, to maintain the same V, because the speed is coming lower, I need to have a higher angle of attack, which means the blade has to be twisted quite a bit. As you can see in the right extreme triangle, it's a smaller angle, the dotted line making with the U, and there you can see it's a larger angle, which means the blade aerofoil has to be twisted. As there is a small blade which I brought it along, you can see outside what I mean by this concept of needing a twist to maintain more or less uniform velocity. This is giving a cross-sectional detail of the blade, showing the blade angles at various locations from the tip on the right extreme to the shoulder, where you have the maximum aerofoil and you can see them twisted physically. This is one view from the tip of the blade to the shoulder of the blade, how these aerofoils will look. At the tip you need smaller aerofoil, at the shoulder you need a bigger aerofoil. The importance that we have been able to get in this kind of aerodynamic design is not able to achieve in the metallic blades, because most of the metallic blades, when you twist them, fixing them to the hub portion becomes a problem. So these are made with constant carbide, and constant carbide because they're trying to overcome the probability of not being able to twist the blade, because the blade fails if you twist the metallic portion because of its own metallic limitations. Whereas in the fiberglass, you don't have that kind of a problem. When you mold it precisely and accurately, you can twist the blade to the maximum angles that are required as per your aerodynamic design and still be in a place, as you will see in some of the designs that we will talk. This we have already discussed. and obviously the whole thing depends on the blade area, dynamic pressure, and the coefficient of lift. This coefficient of lift, as we call CL, is very, very important for finding out the total weight that can be utilized by the blade. This is the drag about which we already spoke of. And there are certain simplifying laws, although they are not very complicated, but one needs to understand these things basically because, as you can see, the power varies as cube of the speed. So some people think that why don't we just increase the airflow by increasing the fan speed? Then obviously your motor will be a limitation. So other than that, you find that some of these aerofoils that you have, they have a limitation of something called a stalling operation, which most of the operation people get into. What they do is, if the fans are operating at a particular angle of setting, they say that, oh, we need more airflow and we seem to have the motor capacity, so why don't we go on pitching up the blade angles? Once you go on pitching up the blade angles, there is something called stalling that is occurring in these blades, depending on the blade design. Then, although the power consumption goes up, because that's what anybody in the plant would do, whether your amps have gone up or not, but without the knowledge that the blade has already stalled and it's actually recirculating there, right there, rather than sucking it through your system. So it's not always that just keep a close watch on the motor power and go on increasing